In this lesson, you'll identify and graph step, constant, and identity functions, and identify and graph absolute value and piecewise functions. How do step functions apply to postage rates? The cost of the postage to mail a letter is a function of the weight of the letter, but the function is not linear. It is a special function called a step function. I used GeoGebra to graph this particular step function. You can see that for the values between, well, that should have been or equal to probably on the 0 because every piece of mail is going to weigh something. Between 0 and 1, the postage is 34 cents. So I've got an open circle on 0 because it shouldn't equal 0, closed circle on 1. And then between 1 and up to 2 ounces, it's going to cost 55 cents. So we jump up. So from 1 up until we get up to, it says not over 2 ounces, so it can equal 2 ounces, so it's a closed circle on the right. And then not over 3, it jumps up to 76 cents. So open circle on the left, closed on the right. And between 3 and 4 ounces, so open circle on the 3 because it's jumped up until closed circle on the 4, it costs 97 cents, or it did when this was copyrighted in 2005. The graph of a step function is not linear. It consists of line segments or arrays. The greatest integer function written f of x equals greatest integer of x is an example of a step function. The symbol greatest integer of x means the greatest integer less than or equal to x. For example, the greatest integer of 7.3 is 7, and the greatest integer of negative 1.5 is negative 2 because negative 1 is greater than negative 1.5. Okay, so spend some time looking at the table in the graph below, and I will also put a GeoGebra file that shows greatest integer function that you can play with in your Google Classroom. So the big idea on the basic greatest integer function is we're going to always have closed circle, open circle. So the dot means that the point is included, the open circle means that it is not. Notice that the domain of this step function is all real numbers, and the range is all integers. One psychologist charges for counseling sessions at a rate of $85 per hour or any fraction thereof. Draw a graph that represents this solution. Okay, so if you are in counseling for anywhere from 1 minute up until 60 minutes, you pay $85. But if you're there 61 minutes, boom, you're paying $170. So the graph of this situation, they've labeled the vertical axis every $85. That makes sense. He's charging $85 per hour. And the horizontal axis is our time in hours. Okay, the book starts off with the most challenging function first. The next one is the easiest. It's the constant function. You learned in lesson 2.4 that the slope-intercept form of a linear function is y equals mx plus b, or in functional notation, f of x equals mx plus b. When m equals 0, the value of the function f of x is b for every value of x. So f of x equals b is called a constant function because it doesn't change. If we wanted to make a table of values to graph this, if x is negative 2, y is, oh, there's no place to put the x, it's negative 3. If x is 0, y is still negative 3. If x is 2, y is still negative 3. I don't care what you put in for x, you're going to get negative 3 for y. The graph of that is going to be a horizontal line. Slope is 0. Another special case of slope-intercept form is m equals 1, b equals 0. This is the function f of x equals x. The graph is a line through the origin with a slope of 1. Since the function does not change the input value, f of x equals x is called the identity function. You are who you are. Another special function is the absolute value function. F of x equals the absolute value of x. So if we put in -3 for x, we get out 3, -2 gives us 2, -1, 1, 0, 0, and then we repeat the process. 1 is still 1, 2 is still 2, 3 is still 3. So this function ends up looking like a nice little v. Notice that the domain is all real numbers, and the range for the absolute value function is all non-negative real numbers. Graph f of x equals the absolute value of x minus 3, and g of x equals the absolute value of x plus 2 on the same coordinate plane. Determine the similarities and differences in the two graphs. For the f function, if x is 0, 0 minus 3 is -3, the absolute value is 3. 1 minus 3 is -2, the absolute value is 2. 2 minus 3 is -1, the absolute value is 1. 3 minus 3 is, of course, 0. And now we're going to start repeating. 4 minus 3 is 1. 5 minus 3 is 2. For the g of x function, if we put in -4, -4 plus 2 is -2, the absolute value is 2. -3 plus 2 is -1, the absolute value is 1. -2 plus 2 is, of course, 0. And now we're going to start repeating. -1 plus 2 is 1, the absolute value is 1. 0 plus 2 is 2, and 1 plus 2 is 3. And then we get a plot. And of course, when we plot points, if we're going for the first function, 0, 3, 1, 2, 2, 1, 3, 0, 4, 1, 5, 2. They look like they're the same shape. They both have the same domain, all real numbers. They both have the same range, y is greater than or equal to 0. They're the same shape, but they have different x-intercepts, where they cross the x-axis is different. The graph of g of x is the graph of f of x. We could say translated 5 units, 1, 2, 3, 4, 5 units to the left. The absolute value function can be written as f of x equals -x if x is less than 0, or x if x is greater than or equal to 0. A function that is written using 2 or more expressions is called a piecewise function. So just like when we graphed those two absolute value functions, we're just going to put both graphs on the same grid paper. Identify domain and range. 3 is an important number on this graph. It's in both of the if parts, restricting the domain. So if I put 3 in for x, 3 minus 1 is 2. I can plot the point, 3, 2, and then from there I know my slope is 1. So I can go backwards, down 1, back 1, and there's that line. And then the second part says f of x equals -1 if x is greater than 3. So I need an open circle at 3, -1, and it's going to stay there. It's a constant function. So open circle, arrow goes to the right. The graphs of each part of a piecewise function may connect, as in the absolute value function, or they may not, like in example 4. A graph may stop at a given x value and then begin again at a different y value for the same x value, like we did in that example. The last thing we need to do is the easiest, is just to be able to identify which kind of special function it is. So here's a nice summary, so we make it easy to identify. A step function, we've got just a bunch of rays or segments. Constant function, horizontal line. Absolute value function looks like a V. And the piecewise function, we have different rays, segments, and or curves. Determine whether the graph represents a step function, constant function, absolute value function, or piecewise. Well, this one's in pieces, so it is definitely piecewise. This graph makes a V, so it looks like a absolute value graph. Straight line, so this would be the constant function. Oh, that's another absolute value. Where's the step function? Oh, well, there wasn't one in the PowerPoint for me to steal. So, hey, there it is. Brought in the one I made in GeoGebra. Here again are the 4 special functions we went over in this lesson. the greatest integer function, which is a step function, the constant function, which is a horizontal line, the absolute value function looks like a v, and the piecewise function is made up of pieces of little functions.